Howdy everyone, I'm Aroma and I'm here today with Sourav and Pushp and we'll be presenting our project on Perceptron based prefetch filtering. We know that cache is a faster memory that sits between the processor and the main memory. Different architectures employ multiple levels of caches as we can see in this diagram. L1 cache is the one that is closest to the processor, and then we have the L2 cache and the last level cache. The cache size and the access latency of the cache levels increases as we go away from the core. We also know that cache misses are expensive. That is why we need prefetchers to better hide the memory latency in all modern designs. A cache prefetcher monitors the access requests that are sent to a cache level by the processor, and based on these access patterns, it tries to predict what would be the potential next accesses. And then it issues the prefetch request for these accesses much before the actual demand request is made by the processor. Now we understand that prefetchers are necessary, but there is a limit to on how much aggressive the prefetcher can be. As we can see in the first graph here, where we are comparing the amount of prefetch requests that are made by the next line prefetcher as we increase the degree. We can see that as we increase the degree, the number of prefetch requests made by the next line prefetcher increase rapidly. However, the number of useful requests made by it do not rise at the same rate. So effectively, as we increase our degree, the difference between the useful request and the prefetch request sent out by the next line prefetcher increases. This ultimately starts to hurt our performance. If we compare the IPC of the next line prefetcher along with its degree, we see that the best IPC is achieved at a degree of 3. And as we keep on increasing the degree, the IPC of the next line prefetcher goes down. So, our project is Perceptron based cache prefetching, in which we implement a second layer of filtering over an existing baseline prefetcher. This Perceptron layer filters out the useless prefetch requests that were made by the baseline prefetcher, and thus it decreases the total number of prefetch requests that were made. As we can see in this graph, where we have compared the prefetch requests made by the next line prefetcher and as compared to the prefetch request made by a next line prefetcher with Perceptron filtering. We observe that as we increase the degree of prefetching, the number of requests made by the next line prefetcher increases rapidly. However, the number of prefetch requests made by the next line prefetcher with Perceptron filtering are way less than the one made by just the next line prefetcher. So overall, this helps us to reduce the amount of bandwidth that is consumed by our prefetcher, and it also helps us to increase the accuracy. If we compare the IPC of these two prefetchers, as we saw in our previous slide, that the IPC of the next line prefetcher decreases as we increase the degree of prefetch. However, if we see the numbers for the next line prefetcher with Perceptron filtering, we observe that the IPC of this increases as we increase the degree. Before going into the details of the Perceptron filter, let's have a look at the baseline prefetchers that we are using. First up is the next line prefetcher. The next line prefetcher simply prefetches the next D lines of after a miss, where D is the degree of aggressiveness. In case of the IP stride prefetcher, this prefetcher first determines the stride based access pattern, and then based on that pattern it prefetches the next D lines. Then finally we have the SPP-Dev prefetcher, which is the most sophisticated of all three. This one is a confidence-based look-ahead prefetcher that maintains a signature of each prefetch series. And unlike the other two prefetchers, SPP-Dev is able to look beyond the page boundary, and thus it produces better prefetches. So overall, we have implemented our Perceptron filter over all of these three existing designs. So first we have the next line prefetcher with Perceptron filter, which we'll refer to as NLPF. Then we have the IP stride with the Perceptron filter, which we'll refer to as ISPF. And finally, we have the SPP-Dev with the Perceptron filter, and we'll refer to that as SPPF. The inspiration for our project is taken from the work done by E. Bhatia and others in their paper titled Perceptron-based prefetch filtering. In their paper, they implemented a Perceptron over SPP-Dev prefetcher. For our project, we have extended this idea to other baseline prefetchers, nextline and IP stride as well. Before this, something similar was done by H. Wang and Z. Law in 2017 in their paper Data Cache Prefetching with Perceptron Learning. However, their baseline prefetcher was a stride or a Markov prefetcher. The original idea for the Perceptron was described and implemented for branch prediction by Professor Daniel Jimenez in 2001. This perceptron model proved highly effective for branch prediction. That is why there are latest works where people are trying to implement a perceptron model on cache prefetching to better improve the performance.
Now we'll be talking about some of the metrics that we use to evaluate a prefetcher, namely accuracy, coverage, bandwidth, and performance. Prefetch accuracy is the measure of how accurately memory addresses are bought into the cache, whereas coverage is the fraction of cache misses that the prefetcher prevented. These two parameters are orthogonal, however, as even though an overly aggressive prefetcher will prefetch too many lines, increasing the coverage but reducing the accuracy. It might even increase demand misses by replacing useful cache blocks with prefetch data, eventually hurting performance. Next parameter is bandwidth, which is described as the total number of prefetch requests made by the prefetcher. And finally, we have performance or speedup, resulting due to prefetcher, and is described here as the ratio of IPC between our model and the baseline. Over here we can see the top level working model of our design. In the center we can see the baseline prefetcher. This prefetcher can be anything. It can be IP stride, next line, and SPP-Dev that we have used, or any other prefetcher that we want. This baseline prefetcher monitors the access pattern from the L2 cache and sends a prefetch suggestion to the PPF filter. This PPF filter can now take the prefetch suggestion and the prefetcher metadata and decide whether to prefetch this line or not. If it decides to prefetch it, it can be sent to the L2 cache or LLC cache based on the metadata. As we will see in the later slides, that baseline prefetcher can be made more and more aggressive to improve the performance and accuracy of the design, and the prefetch metadata from the baseline prefetcher can be used to train our PPF. Looking into more details about our complete model, we have a baseline prefetcher that will suggest a prefetch line based on the cache access pattern. The metadata of this suggestion is used to index into a set of feature tables. These feature tables have 5-bit saturating counters. The metadata used here can be instruction address, prefetch request address, etc. Each table has different number of entries based on the type of metadata that is used. Summing together the index weights along with the bias, we check if it exceeds the set threshold in order to determine if the final prefetch decision is true or false. And there is a transfer buffer here which keeps track of all the recent prefetch decisions made by our model. Next, let's briefly talk about the training model of our Perceptron. Unlike in branch prediction, the correctness of prefetch decision cannot be known immediately, and we must wait for a cache hit event to know the prefetch usefulness. Thus, we define two scenarios to decide the training of our Perceptron. We will retrain the weights of our Perceptron positively, that is, increment the corresponding counters whenever we find a hit in the cache that was initially suggested by our prefetcher. So, we reaccess the transfer buffer metadata for retraining, and in the second scenario, we train the Perceptron negatively whenever an older entry in the table is ejected by a newer entry, since it indicates that the entry was probably useless. During these two training models, our neural network becomes capable of distinguishing useful prefetches from the useless ones. Here we can see some of the features that we use to train our model. This include instruction pointer, prefetch address, degree of prefetch, and other page related stuff. Here we can see some of the evaluation setups that we use to simulate our design. We have a single core CPU of 4 gig frequency and 352 ROB entries. It's a 4-wide machine with a lower level cache of 2 MB and L2C cache of 512 KB. We have a Y-model branch predictor, and we have used a simulator of ChampSim. We have 19 workloads of 2017, and our prefetcher is on L2C. As we've already mentioned, we have 3 types of baseline prefetcher: IP stride, next line, and SPP-Dev. This slide here serves as an example of how we'll be evaluating our design across different benchmarks. Here we can see that we have 19 of the Spec 2017 benchmarks, across which we have plotted the accuracy of the next line prefetcher with a degree of 9 and the next line prefetcher degree 9 with the PPF filter. As we can see, that accuracy is mostly increasing, and in the last column we have plotted the average accuracy, which has a overall increment. So in the next slides, we'll be only talking about the average of accuracy, coverage, and bandwidth, and we'll be taking the geomean of the performance across different flavors of Perceptron filter and prefetchers, like different degrees and different stride lengths.
Let us now analyze the results across different prefetcher designs. We are varying the degree of our baseline prefetches to see the results. First up, let's have a look at the next line prefetcher. The baseline next line prefetcher is very naive in the sense that it simply prefetches the next few lines. So our Perceptron is able to increase its accuracy by more than 10%. To achieve the same amount of accuracy from IP stride, we had to use multiple new features because the IP stride prefetcher is relatively smarter in the sense that it finds the access patterns first. On the other hand, the SPP-Dev is the most complicated of these three prefetchers and exhibits a very high accuracy from the baseline prefetcher itself. So multiple new features and some careful tuning of thresholds and parameters was required to achieve better accuracy from SPP-Dev. Let us now have a look at bandwidth. Here we show the number of prefetch requests in millions. As expected, number of requests have reduced in all these designs. The biggest reduction is seen in the next line prefetcher, which is around 75%, followed by SPP-Dev, and at last we have IP stride. It is important to note here that the number of requests made by the IP stride prefetcher is less as compared to the other two prefetchers, due to which it has more time to stay in the transfer buffer. So the longer the request stays in transfer buffer, the higher the probability of it to be designated as useful. Therefore, the filtering done on the next line is the highest and the filtering done on the IP stride is the lowest. Next, we have coverage. We represent our results as percentage improvement in coverage over a design without any prefetcher. This slide is quite interesting because all our designs are exhibiting completely different trends. Let us analyze why. The first one is next line. The next line prefetcher, as we know, sends in a lot of requests for prefetching data, and these requests get multiplied as we increase the degree. So due to a larger number of requests that are coming into the cache, this data is knocking out some of the existing cache lines, due to which the cache misses are actually increasing, and as you can see in this curve, the coverage is decreasing as we increase the degree. The Perceptron is able to figure this out, and it is able to filter out the useless prefetches, and with the increase in degree, we see an increase in coverage. SPP-Dev shows a similar trend to the next line, because SPP-Dev again is a very aggressive prefetcher and sends a lot of prefetch requests. Similar trend is observed by the SPP-F here, and the coverage increases as we increase the degree because filtration is more accurate now. The last is the IP stride. In the IP stride, it is important to remember that the prefetch requests that were sent by IP stride were less as compared to the other prefetchers, due to which when we increase the degree, the knocking out of the data is not as pronounced as in the other prefetchers. Due to this, the coverage is increasing for the baseline IP stride when we increase degree, and the same trend is being followed by our ISPF. The coverage increases with the increase in degree, and as we see, we are catching up to the baseline prefetcher with the increase in degree, because now now the pollution has started increasing, and Perceptron is more effective in these areas. So our aim of increasing the coverage of a baseline prefetcher without incurring any penalty on accuracy is achieved with the help of Perceptron filter, because we can now allow more prefetch requests, but we filter out the useless prefetch requests. This is where we present our performance results. To compare the speed up, we have normalized the IPC of all these designs with respect to a no prefetcher design. When we increase the degree of aggression of our baseline prefetchers, we see a degradation in performance of SPP-Dev and next line prefetchers. This is due to an increase in cache pollution. With Perceptron, the trend is the opposite. When we increase the aggression, the performance is increasing because the coverage is increasing. This trend is not exactly followed by the IP stride, because again the IP stride issues very less requests and the pollution is very less. But the Perceptron performance is increasing with degree, and we expect that if we increase the degree even further, or if we allow our IP stride to prefetch across page boundaries, we expect a similar performance that our IP stride with Perceptron filter will eventually better the baseline IP stride. We found a very interesting thing while evaluating our ISPF during initial stages. As we can observe in these two screenshots, these are the excesses made by the original IP stride, and these are the excesses made by the Perceptron IP stride. As we can see, all the requests made by the baseline prefetcher are filtered out here, and there's no request that is being sent to the memory. So we tried this experiment by varying the weight sizes, by varying transfer buffer size, having new features, deleting some features, but the result was always the same. This is when we started probing further, and we found that there was a fault in the IP stride code, and it was accessing some data which was not relevant. So this shows how effective our Perceptron is in filtering out these kind of useless prefetches.
To summarize the results of our project, we now know that coverage and accuracy are orthogonal to each other, and if we make our baseline prefetcher more aggressive, it sends out a large number of prefetch requests. So coverage increases, but at the cost of accuracy and high bandwidth consumption. This is where our Perceptron-based prefetch filtering comes into the picture. It decreases the number of prefetch requests that are sent out by the design, thereby reducing the bandwidth consumed by the design and increasing accuracy at the same time. We also observe an increase in the coverage for Nextline and SPP-Dev because the Perceptron filters out the useless requests. However, there is a slight reduction in accuracy in coverage observed for IP stride because the total number of requests sent out by the IP stride baseline prefetcher is less. Since we know that the Perceptron is not a perfect filter, we observe a slight decrease in the IPC for IP stride and SPP-Dev baseline prefetchers. However, if we compare the IPC of a lesser aggressive prefetcher with that of a highly aggressive baseline prefetcher with Perceptron filtering, we observe that those IPCs are similar. One of the major advantages of using a Perceptron filter is that it can be used with any baseline prefetcher to improve its metrics with slight feature training. There's a lot more research that can be done on Perceptron-based filtering. One of the most important things is to experiment with different features. Feature tuning still remains a mystery, and there's more work ongoing in the academia on this. We can also design better retraining algorithms and experiment with varying hardware resources allocated to the Perceptron filter. Additionally, we can increase the size of the transfer buffer so that the accessors have more time to be assigned as useful. We can also try to implement this on multiple levels of caches and tune the Perceptron according to each level separately. Finally, we can experiment on multi-core designs and add more benchmarks for better evaluation of the results. We hope you enjoyed our PPT. Thank you for your time.